Today's enjoyment is courtesy of integration. We're going to be working through some past paper questions using those tips and tricks and techniques that we talked about in the theory lesson last week. So I've got a selection of past paper questions. We have a limited number of questions we can do in 30 minutes, but hopefully this will give you a good idea of the spectrum of questions and we'll touch on all the different techniques. Starting off from summer 2016, we have a curve is such that dy by dx equals 8 over 5 minus 2x all squared. Given that the curve passes through 2, 7, find the equation of the curve. So this is one of those where we're going from a derivative back up to a curve. So we're just simply reversing the differentiation. In this case, we've got a function here that is not in calculus format. So we're going to have to do some playing with that as well. And then we're going to be working up to y and then using our point to get our particular solution. So we want to start by rewriting our derivative in calculus format. So we bring that up from the bottom and give him is minus 2. We double check. This in here is linear. We have ax plus b to the n. So then we are ready to go ahead and get our general solution. Okay, so we want to then integrate. We're going to have a y equals. So in this case, we don't worry about the integration notation using the integral sign and the dx because we're simply reversing from a dy to a y. But as we integrate that side, we have to integrate the other side as well because we must always do the same thing to both sides of an equation. So when we integrate this, our 8 stays. 5 minus 2x stays exactly the same. Minus 2 plus 1 gives us minus 1. Then we're going to divide by our new index, so minus 1. And we're going to divide by our coefficient of x, so minus 2. Always remember to take that sign. Whenever we integrate and we're not working with limits, then we must have a plus c as soon as you integrate. So we've gone from dy by dx to y. We've gone from our derivative term to our function term, and then we've added a plus c to account for that constant. Next step is always to simplify. So y equals 8 divided by 2 is 4 times 5 minus 2x to the minus 1 plus c. And we are aware that the next thing we're going to do is we're going to look at that particular solution, which means we're going to be doing a bit of algebra. So we want this now in algebraic form. 4 over 5 minus 2x plus c. Now we're ready to calculate that value of c using the point that they gave us. So for particular solution, making it clear exactly what is going on, 7 equals 4 over 5 minus 2 by 2 plus c. So 7 equals 4 plus c, c equals 3. And we don't stop there because they didn't ask us what's the value of c. They asked us for the equation of a curve. So our final answer, equation of the curve, is y equals 4 over 5 minus 2x plus 3. So because we were given originally dy dx, then our equation has y equals. We're working in that y dy dx notation frame of mind. So that is your simple and straightforward, working back from a gradient function to a function using a point on the curve to locate that particular solution. Our next question, you can see straight away, we're working with a different kind of notation. We have a curve that has equation y equals fx. It's given that f dash x is x to the minus 3 over 2 plus 1, and that f of 4 equals 5. Find fx. So this sounds remarkably similar to the question we just did. The difference here is that we're working with a different notation. So we have f dash x equals x to the minus 3 over 2 plus 1. We are already in calculus format. We have ax plus ax to the n, we have a constant. So now we can go straight into for general solution. If we are integrating from f dash, we're going to integrate to f of x. If we integrate one piece, we have to integrate the next. So x to the minus 3 over 2 becomes x to the minus a half because we've added 1. We then divide by minus a half, so we times by minus 2 plus constant times x. 1 times x is x plus c. Never forget that constant. So now we have fx equals minus 2, x to the minus a half plus x plus c. This is not totally in algebraic form. It's minus 2 over root x. But see how we got the same format as we had in the question. So we're good to leave this one here. And we don't have to simplify. We can go straight into for particular solution. And this is why I say it's so important to be comfortable with function notation. Because now we need to think about this. f4 equals 5. So instead of having fx, we would have 5 equals minus 2. Where we have x's, we put 4's. So minus a half plus 4 plus c. So 5 equals minus 2 over 2 plus 4, that's minus 1 plus 4, which is 3 plus c. So c equals 2. Nice and straightforward. So now we've got everything we need to do our particular solution. Therefore, fx equals minus 2, x to the minus a half, plus x, plus 2. So a very similar thing, working from a derivative back up to a function, but doing it now in function notation. So we have our f dash and our f of x rather than our y and dy by dx. So it's really important that you maintain that flow through your answer, that you're using the right notation that applies to the question, and that you're understanding how the function notation turns into the different values, that you don't get your 4's and your 5's mixed up. So make sure that you are happy with function notation coming into calculus, because it's really important as you work through. Function notation is not going to go away anywhere. It's going to keep coming back. Moving on to something slightly different, looking now at an area calculation. So here we have a diagram showing a curve, an unhappy quadratic, and a straight line. Find, showing all necessary working, the area of the shaded region. If you do not show all your working, you can lose marks for these very quickly. We have two intersections here, this one and this one. So we're going to need to know where those are, because that's our limits, A and B, for our integration. Remember, when we do area under a curve, if we're doing area between two, we've got two options, when we have one intersection or when we have two intersections. When we have two intersections, we want to combine these first, then integrate once. So let's lay out where we're going. Area equals integral from A to B of top minus bottom dx. Yes, it is very technical terms, top minus bottom, but what this is doing is it's setting up exactly where we're going. It's helping us keep on track of what we need to do. So the first thing we get to that's a problem in our lives already is what are our limits? So the first thing we need to do is find them. Limits are the two intersections. Intersections we always do by simultaneous equations. Nothing has changed there. So 2x plus 1 equals minus x squared plus 12x minus 20. That intersection, that simultaneous solution is going to give us our two limits. So we bring them all to a happy x squared because he's nicer to deal with. X squared minus 10x plus 21 equals 0. Factors of 21 that are going to add to give us 10. Well, that's nice and simple, 7 and 3. Equals 0, never forgetting our equals 0. Nothing's changed there either. Like signs, and both are negative. So x equals 3 and x equals 7. That's our two limits. The next thing we need before we can calculate our area is this top minus bottom. So we're going to call that a combined function. So top minus bottom. In this area here, our curve is on top and our line is underneath. So we would need curve minus line. So minus x squared plus 12x minus 20 minus line in brackets 2x plus 1. It's a simple little addition, but what it means is that you protect those signs of that line, and when you now do everything and you incorporate it all together, you know you've got the right signs going on. So minus x squared stays as is, plus 12x minus 2x is plus 10x, minus 20 minus 1 is minus 21. So there is our combined function that now we're going to work with for our integration. We have our limits, we have our top minus bottom, so now we are ready to do our area. So that statement at the beginning really works like a shopping list of what we need to work through in order to get to our final answer. And those sorts of shopping lists are fantastic in maths, especially when you get to longer questions. Okay, so for the area, we now know that we need to give ourselves some space for this one. Area shaded equals the integral from 3 to 7, our limits, of minus x squared plus 10x minus 21 dx. So we have our function, we have our limits, we have our dx. Everybody's already in calculus format, so we can go straight into our integration, which means we go straight into our square brackets. Minus x squared, so 2 becomes a 3, divide by the 3, so minus a third, x cubed. Plus x squared, divide by 2, so 5x squared. Constant gains in x. No plus c because we're dealing with now a definite integration. Other end of our square brackets and our limits, 3 and 7. Now remember how they said that you must be sure to show all your working? That means that you must be sure to show the substitution of your limits. So we need to show minus a third, 7 cubed, plus 5, 7 squared, minus 21, 7. Minus, then we insert our lower limit. Minus a third, 3 cubed, plus 5, 3 squared, minus 21 times 3. And there is that ever so important for method marks, clear substitution of our limits. Now, I like to take it one step further. This is quite a lot of calculations, quite a lot of things going on. So I prefer to do one bracket, then change the value and do the other bracket. So in the first bracket here, if we plug all this into a calculator, then we get minus 49 over 3. Minus, in our second bracket, all of this brings us to minus 27, which takes us to 32 over 3. So it's rather a massively top-heavy fraction. So let's take this one down to 10 2/3 units squared. Okay, because when it's massively top-heavy and it's a final answer, then there's not so much of a query as into why we use a mixed number. We're not going to use this value again. So having a mixed number there is fine. So we had a question come through of why we don't have a plus C here. So let's just recap a little bit on why we have no plus C. When we integrate, let's say we got to this stage here. Obviously, this question was meant to be, I've got space to do it. So let's say we integrate and we have plus C with our limits. Okay? Then we substitute in our limits. Blah, 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 blah with a 7 plus C minus blah, 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 blah with a 3 plus C. So then we get the magic, because now we would have minus 49 over 3 plus C minus 27 plus C. Do you agree? Right, so then if we simplify this, we have minus 49 over 3 plus 27 plus C minus C, which is 32 over 3. So whenever we're working with limits, we have that same situation. If we put in a plus C, we end up with plus C minus C, and they disappear completely. So when we're doing definite integration, working with limits, we integrate to our square brackets with our limits, and we don't have to worry about the plus C. Our last question looks at the sort of last element of integration. We've looked at general solutions and particular solutions and our indefinite integration with a plus C. We've looked at calculating an area. So integrating, in this case, we combined our curves and then integrated. Well, combined a curve and a line and integrated for an area. So the last thing on that list of integration things is your volume. So this is an interesting question because this is one of those few and far between. We have a part of a curve. We have a shaded region bounded by a curve, the y-axis, and the lines y equals 1 and y equals 2. So alert systems are ringing. Showing all necessary working, find the volume in terms of pi when this shaded region is rotated through 360 degrees about the y-axis. So we are rotating around the y-axis. We are not working with respect to the x-axis. So just like we did with the area, we want to start out with that shopping list. We're going to now be dealing with volume equals pi times the integral from a to b of x squared dy. That's where we're heading to. That's how we get our final answer. So then we can work through what do we have and what do we still need to figure out. Pi is pi, is not going to change. A and B are our limits, and there they are, 1 and 2. They're given to us. X squared, we do not have. So x squared is the one we're going to have to figure out, dy. So we start out with, for x squared, we know that x equals 12 over y squared minus 2. Algebra, my darlings. Your algebra means x squared, laws of exponents, laws of equations, 12 over y squared minus 2 all squared. And this is where it so often falls apart for the volume calculations. It is all squared. You must square that whole entire side. So if we do so, we get x squared equals 12 over y squared times 12 over y squared. So 144 over y to the 4. Whoa, that's a little bit big. Okay, exponents must be lifted. Okay, minus 2 times 12 over y squared, so minus 24 over y squared, and again minus 24 over y squared plus 4. If you have to write out the two brackets in order to work through this systematically, then do so. Do not lose marks here, because it's going to knock all your marks further on. Okay, so simplifying. X squared equals, let's actually give myself a bit more space, equals 144 over y to the 4 minus 48 over y squared plus 4. So we have now an x squared. But where are we heading? We're heading from here into integration. We're heading into calculus. So it would be a whole lot more helpful if x squared equals 144 y to the minus 4 minus 48 y to the minus 2 plus 4. Because now each of those three terms is in calculus format. Each of them is now ready for that integration. Got our limits ready, got our x squared ready, so now we can do for volume. So, volume, always do this and then I don't leave myself enough space. Limits require a lot of space along a line. So volume equals pi times the integral. Our limits were 1 and 2, limits on the y-axis. As we're going around the y-axis, 1 to 2. 144, y to the minus 4, minus 48, y to the minus 2, plus 4, integrating with respect to y. Then it's the same thing, equals pi. We're going to integrate, so we go into square brackets. Y to the minus 3, 144 divided by minus 3 is minus 48. Y to the minus 1, minus 48 divided by minus 1 is plus 48. And a constant gains a y. Remember, you are going with y's. It's all about y's. There's no x's here. Y, 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 y. Okay, so we have our integrated function. We have our pi sitting waiting. Now we go for our limits. Being careful to keep that pi attached to everything. So I like to do it by keeping in a square bracket. So minus 48, 2 to the minus 3, plus 48, 2 to the minus 1, plus 4 by 2. Closing off the bracket for that limit, minus, opening a bracket for the other limit, minus 48, 1 to the minus 3, plus 48, 1 to the minus 1, plus 4 by 1. Closing off the bracket for that limit, closing off the square bracket for the pi. So now we know that the pi is going to multiply in over everything properly. And yes, 1 is 1, minus 1 is minus 1. Okay, it's not going to change anything with these minus 3s and minus 1s. But what we want to do is we want to show that we know how to substitute those limits properly. So even though it might seem a little bit silly at times, you must show that full method of, this is how I use my limits. Substitute them in, and remember all your brackets. We can then simplify. So we get equals pi. Leave the square bracket there to remind you of what's going on. Our first bracket goes to 26 minus, and our second bracket goes to 4. So 26 minus 4 is 22. 22 times pi is 22 pi. Whenever we're doing volume calculations, we always want to give that final answer in terms of pi unless told otherwise. It's one of those, another points where we're looking for accuracy because we're dealing in pure maths. So same like we leave surds in answers, we leave pi in our answers as well. So we've gone from that initial shaded area, rotating around the y. We used our shopping list to figure out what it is that we need for this question. Then we systematically work through it and calculate the volume to be 22 pi.